Hello, my name is Anke Hagen. I'm a professor at the Technical University of Denmark. Welcome to my lecture, Catalysts. I will start explaining what are heterogeneous catalysts. Then I will point to or explain some methodology for catalyst characterization and talk about catalyst deactivation as well. Let me start by outlining the types of catalysts you find. We classify them in homogeneous catalysis, where catalyst and reactants are in the same phase, could be the liquid phase. Typically, you work under quite mild reaction conditions, often in aqueous media, means below 100 degrees centigrade. After the reaction is completed, you have to separate catalyst and reactants, which might be an elaborate process, such as distillation. One specific case of homogeneous catalysis, you can say, is enzyme catalysis. That is also typically in the liquid phase, happening in your body, in nature, where you often have very specific catalysts called enzymes that only allow one species to interact and to react to a very limited or only a single product. Also here we have these quite mild reaction conditions and often specialized for one or two products only. The third category is heterogeneous catalysis, and that is actually the most important seen from an industrial perspective. Most of the industrial products we have in our daily life have involved steps of catalysis in their production routes, and that's why I today focus on this catalysis. Characteristics are that the catalyst and the reactants are in two phases, could be the gas phase reactants, the catalyst in the solid phase, which makes it very easy to separate them from each other, and you can also run a continuous process and reuse the catalyst for quite some time. The heterogeneous catalytic process consists of quite many steps. Often you start from the catalyst palette, shown here on the left-hand side, which has some centimeter, 10, 20 centimeter size. And when you zoom in, you will see that in the pellets you have channels and pores, and within the pores you have the actual active sites that do the catalysis or that are responsible for the catalytic effect. In this illustration, the black dots, these are the active particles, and they should represent noble metals in that case. So you can define quite many processes that are proceeding during a heterogeneous catalytic process involving transport among the or around the pellets, into the pellets, into the channels and pores towards the active sites, where there is an adsorption of reactants going on, then your desired reaction, and then all the way back a desorption of products and then transport back. So quite many individual steps. Just to show you a real-world example from photos or microscopy, you have here pellets, and then zooming into the micrometer scale, you see the black particles that are the active sites or the noble metals. Most important for the catalytic process and for the lecture today is the catalyst, and here in particular adsorption, surface reaction, desorption are key elements, and I will zoom on that a bit further with this illustration. So you have a transport of your species that interact with the surface, undergo a reaction, and then are desorbed. That means also for a heterogeneous catalyst, you have the following characteristics. The active sites are only at the surface and only the accessible surface for the reactants. You can achieve selectivities that are medium to high towards the desired product among a larger range of products that might be possible. You can have diffusion issues, transport limitations if, for example, the pores are too small. And the reaction conditions are typically at higher temperatures as compared to homogeneous catalysis. If you need surface atoms and specific interactions or interaction strength between the reactant and the surface, how do you design your catalyst? You have more or less two parameters you can tailor. One is the materials choice, and second is the structure. Materials choice is something about chemistry, and the structure is, of course, how the surface looks like. And here is an illustration of these parameters you can tune. At first, you have to choose the bulk material that could consist of different elements or oxides, like iron oxide or aluminum oxide, silicium oxide. That gives you the bulk structure and gives you the general electronic properties that gives you a certain nature of interaction between your reactant and the catalyst. However, most important is not the bulk as such, however, the exposed surface. That means you have to try to achieving the right morphology of the surface. Often you want to have a very big surface area, because big surface area means many sites potentially to interact with your species. Sometimes you need specific metal planes to be exposed, or kinks or steps, not just a plain surface, to be able to induce the right interaction between your reactant and the surface. So here structural or structuralization plays a major role and imply the right structures. Furthermore, it could be needed that you need specific surface groups. That could be OH groups, they will also call them functional groups, which, for example, could give you some acidic properties like this OH group. If that is able to donate hydrogen or proton, then you could actually use this heterogeneous catalyst as a kind of acid. So we all know hydrochloric acid and sulfuric acid, a lot of challenges in the liquid phase. Imagine we can have similar acids just in the solid state. So they are quite good to handle in large-scale processes. So you have, in general, the bulk material you have to tailor with a certain structure, certain chemical physical properties. You have to fine-tune the structure, morphology of the surface, and you have also to have control of the surface or functional groups. So this is quite a complex challenge that you have to solve to arrive at the right catalyst. And that has been actually solved for many processes, and these are just very few examples of large-scale heterogeneous catalysis processes together with which catalysts are being used. One very prominent is the ammonia synthesis via the Haber-Bosch process, where we use iron-based catalysts that are promoted by potassium oxide and supported on aluminum oxide and calcium oxide. Other examples are steam reforming to make synthesis gas for further on arrive at hydrocarbon products. Here we have actually nickel, a metal supported on aluminum oxide. And so you can go further in the row. Here for cracking, we're using zeolites that are alumosilicates with a very certain specific channel and pore structure. For the ethylene oxide production, we are using silver supported on alumina. For sulfuric acid, we have vanadium oxide supported on silica. Then for nitric acid production, we have platinum-rhodium catalysts, based catalysts. And another one, probably also quite well known, is the three-way catalyst in the cars that also supported noble metals. What is also seen here that there is a huge range of natures and types of catalysts that are around in heterogeneous processes or catalyzed processes. We have, for example, noble metals, like here based. They are often supported on a structure, like aluminum oxide or oxidic structures to have a high surface area and get the good dispersion of those. Or like here, silver supported on alumina. Here, zeolite-based are just the oxides themselves that are active catalysts with a certain functional group towards the surface that will interact with your reactants. So these are a few examples of heterogeneous catalysts. And how can I now see what are the properties? Do I have the right structure? Do I have the right functional group? The right topology of the catalyst? Here, characterization comes into play. And again, looking back, what we need to investigate is what is the crystal structure here in the bulk? Are there some inclusions or, let's say, foreign phases inside? We need to find out about the topology. What is the surface? we need to find out the plane orientation of a crystal, what is exposed to the surface, and we need to find about information about these functional groups and how they are they strong or lesser strong acids, for example, if we have OH groups. And as complex as this, let's say, picture illustration is of a catalyst, is the length scale as well. So we are looking from a crystal towards down to almost atomic scale. So these are the length scales that matter for a catalytic activity. So we have to go from, let's say, macro to micro and nano to characterize our catalysts. And how can we do that? We can use a lot of radiation that is illustrated here. So we go from, let's say, from high energy to low energy. And just to give you let's say, a standard. So this is the visible light here. So this is only a very small part of the electromagnetic spectrum. This is what we actually see with your eyes. And then you can go to, let's say, lower frequencies. Then you have IR or heat, that is actually heat, and so forth. And then you can go to higher energy. For example, UV, you know, from solar radiation, it's a high energy. We also know X-rays also have a high energy. And all these radiations you can actually utilize to characterize a solid heterogeneous catalyst. And in the following, I will give you a few examples of the characterization methods. I will start with one, and that is characterizing the surface or the pores, which are important to transport and also to accommodate the active sites. Here we often use adsorption methods, so we take a certain probe molecule that we adsorb on the surface. That can either be a specific or a non-specific one. And then we are just measuring how much was adsorbed at a certain concentration or pressure, and then we are getting a signal which we can translate here. It's a pore size distribution measurement, that the most of this probe molecule was adsorbed at this specific pore size. If, as shown before, let's say the pores and channels have a very diverse size magnitude, can be micropores and macropores. And for each range, you have a certain probe molecule that is good to characterize these pores. We have kind of distinction between micropores, that are those that are below 30 angstroms. Then we have mesopores, and macropores, they are bigger than 1,000 angstroms. And for the small pores, you can easily take a nitrogen, quite a small molecule, so it's easy to penetrate everywhere, and you can measure how much nitrogen was adsorbed, covering the surface and the pores. If you have bigger pores, then actually mercury porosimetry is the method of choice, where you press the mercury into the pores and then from the deposition can calculate the sizes of the pores and also the surfaces. That is quite important to judge transport properties and also to judge where I can deposit my active sites. Now comes a very complex picture, because this also reflects how complex the characterization is. A typical methodology is that you irradiate your sample with a certain irradiation, and then you measure the response. And this reflects how many versions, and that are not even all of them, you can utilize. You can, for example, put a light onto your sample. That is the light microscope. Then you just look at the light after your sample, and then you get your image. You can also irradiate with electrons, with ions, or with neutral particles. And these kind of illustrations are also visible here. And here I show you what you can get as a response then. So if you irradiate with X-ray, that is this kind of symbol, and then you have a scattered signal, and that gives you an X-ray diffraction pattern, which gives you information about the crystal orientation or the crystallinity of your material. There are other examples, like here you are irradiating with electrons, and these electrons can interact with your material in different ways, and depending on what type of response you are measuring. You're getting response either from the surface, either from a chemical state or a bonding state, and so forth. So you get an impression of the nature of the physics of your active site. So you can irradiate with X-ray, electrons, ions, and then you get a whole range of potential responses that you have to measure with a certain detector, and that gives you a wealth of methodology that is being utilized for characterizing catalysts. I don't go into detail. However, if you're interested, the names of these methods are written here. X-ray diffraction is probably a very common method that is really well distributed, and then there are a more specified methodology that require very certain equipment and access to specific characterization sites. What is also kind of, let's say, a bit a common method is related to microscopy or sometimes also infrared spectroscopy. So this is just a very overall picture of when you put a radiation onto your sample and then you are observing the response. Another methodology involves specific adsorption. So you put a certain probe molecule onto your sample and then you measure how your sample interacts with this molecule. And here I'm putting some molecules that can characterize the acidic strength of your sample. I already mentioned you could have functional groups on the surface, OH groups, that are able to nate a proton, so they would act like a liquid acid just on a solid heterogeneous catalyst. For those who are interested, how strong are these acids? Are they very strong like hydrochloric acid or less like citric acid and so on? And for those distinction, you can use probe molecules. Typically, you use a base molecule. It's like titration in the liquid state. Here, you just do it in the gas phase. There are a few basic molecules you can use as a probe molecule, kind of sensor, like ammonia, pyridine, and so on. They all have different sizes, different basic strength. Like here, the basic strength of ammonia is quite high. And then there are a few moderate, lower basic strength. And they also have different interactions because I mentioned the acids hydrochloric acid. In sense of acidic concept, we actually have several types of acid sites. And the ones that involve a proton, like hydrochloric acid, sulfuric acid, they are called Bronsted acid site, after the Swedish guy Bronsted. And they like to give away a proton. And the easier it is, the stronger is this acid. There's also a concept in organic chemistry called Lewis acid sites. And these are sites that would like to accept an electron pair. So there's not at all a proton involved. However, these are also acid sites that catalyze often organic reactions. And if I have ammonia as a probe molecule, ammonia interacts with Bronsted acid sites. It forms this ammonium ions. So it takes the proton from the acid sites, NH4+, and it also coordinates to the Lewis acid sites. So this is a molecule that interacts with both types of sites. That means when I use ammonia as a probe molecule, I can first see how many acid sites do I have, and second, which type they are, and we can also judge about the strength. And I have a short illustration, like this is illustrating a zeolite. And if you have a functional group, OH group, that would be this one. Illustrating this one would be a Bronsted acid site. So this proton is easy to donate to a reactant. And in addition, if I have, instead of a proton, a zinc ion at the same position, that has actually an electron pair that could interact with another basic molecule. So these are the two types of acid sites that we are looking at right now. So how do I now measure what kind of interaction I have between ammonia and this solid catalyst? One opportunity is to look in the IR spectrum, because when molecules interact with a solid, you can see the frequencies of vibrations in the IR spectrum. Here I don't use ammonia, but I use some other. I use actually pyridinium as a probe molecule. And depending on what type of acid site I have, the, let's say, the absorption bonds are appearing at different wave numbers. Then I can look into the literature and the literature would tell me which type of interaction I have at which wavelength in centimeter to the -1. So in that way, by using IR spectroscopy as a detection or detector, I can see what is the interaction between my probe molecule and the acid site. I can distinguish between the nature and also the strength of this acid site. Another a bit more non-specific method is the temperature programmed desorption. Here I actually also adsorb a probe molecule and then look when I heat up, when does it desorb from the site. So the stronger the sites are, the higher temperatures I would need to desorb this molecule, so I can get in interaction strength signal from this type of characterization. And here we have like two zeolite catalysts, one with a Brønsted acid site, one with a Lewis acid site, and then you can see that this Brønsted acid site needs very high temperatures to release the ammonia, which means that would be a very strong acid site. In that way, I can select the right probe molecule to probe the right functional group and the right property, and by detecting either with IR spectroscopy, could also be UV-Vis, or just by heating up, I can also judge types or strength of these interactions and the sites. And then the last method I would like to show you is microscopy. Typically, we are using scanning electron microscopy. We are coming into the micrometer to nanometer range. Here, a very nice picture of a noble metal supported on a zeolite catalyst. The dark particles are platinum, and then on the support, you can also combine this with an elemental analysis, so you know which elements are located at what position. This microscopy gives you a very nice microstructure. Challenge here is that it probes a very small part of the surface. So if you have a palette of 1 centimeter, you only look into like 100 micrometer, and you have to be sure that you are hitting a representative space for that. So in the previous slides, I showed you several opportunities to characterize your surface, the nature, the chemistry, physics, topology, and so forth. And for your specific challenge, you need to select the right characterization method. Of course, there's also this problem of catalyst stability. I mean, does it last forever? Typically not. Typically, even though we say the catalyst remains unchanged in a reaction, it still can be affected by the conditions or by the reactants. Can it last forever, or must it last forever? That's the question. When we are looking into heterogeneous catalysts, then one would say we would like that it doesn't change and it lasts forever, but that is not real. This is ideal thinking that rarely ever happens, that there's no change at all. What you typically see is that the catalyst lifetime can be between a few seconds to several years. And you might say a few seconds, that will never work. However, there are actually reactor designs that can accommodate such a very fast deactivation. So imagine you do a reaction and the catalyst is deactivated in a few seconds and you have to exchange it. And there is, for example, catalytic cracking, which is a large-scale process that utilizes the concept of a fluidized bed, that you always have more or less continuous reaction and regeneration of the catalyst. So you can even live with a few seconds of lifetime. On the other, let's say, extreme several years, that is an ammonia catalyst, then it will be a different reactor design. Here you can have the same catalyst running for several years. So when you judge a catalyst, you are first judging the activity. Does it decrease the activation energy for your desired reaction? Then the selectivity, does it give you the desired product that you want from a potential mixture? However, the lifetime is actually also a very important aspect that also determines how you design your system. And the deactivation can be caused by several processes. I will go into detail in the coming slides. How often you can actually counteract those by either using a specific reactor type or developing the right catalyst, using safe operating windows, etc. Then when the catalyst is dead or used, then you have to consider, can I regenerate it, maybe reuse it, or do I have to replace, dispose it, maybe recycle it? Now I would like to list a few possible processes for heterogeneous catalysts to deactivate. So this is kind of the active catalyst illustrated here, and then what happens or could happen as the activation. One, you can have deposits that cover your catalyst. You could have a thermal sintering so that your single particles are clogging together. You could have a poisoning, that your active sites are covered by impurities or poisons to this specific surface. You could also lose part of your catalyst into the gas phase or just out of the system. I would like to go into these four mechanisms in the coming slides and give you examples on how you can counteract these deactivations. So first, these deposits, you just physically block the surface. So you take a part of the surface out of the equation, and that part is not accessible for your reaction. Could also lose when you are having these deposits, that you are not only blocking a surface, you can also block pores and the transport, and then increasing the pressure drop through the reactor. Examples for that are actually coking. If you have processes that involve hydrocarbons, then you have to observe the carbon formation window from regarding thermodynamics. Is it possible that you form carbon, and can this carbon form under these conditions? And then there are different types of carbon that can form and can block your surface, clog the pores, etc. If that happens or not is often a function of the temperature you use, reaction time, dilution. For example, the less carbon you have in the system, the less is, of course, the tendency that you have carbon deposition. And you can regenerate to a certain extent depending on which type of carbon you have. You could hydrogenate this carbon in a regeneration step or burn off the carbon. Examples for that are coking of reforming catalysts that are typically nickel supported on let's say a large surface area oxide. And here you actually have to try finding safe operating windows that you are totally avoiding the formation of this specific deposit. The next example is the sintering, and that can happen when you have catalysis going on at very high temperatures. It can be that you are forming new phases. It could be that you are growing the same phase so that they are starting to sinter together. You are losing porosity and you are losing surface area. And what you can do against that is that you are making a better catalyst that cannot undergo these reactions. You can add additives or promoters that prevent that your phases can react with each other, or that make your phases more stable. It's of course very difficult to regenerate once you have had phase changes or the sintering together. So you need stable materials and adjust the right operating conditions, maybe stay below a certain temperature to avoid this degradation. The third example was this poisoning. Poisoning means that you can have a gas phase species that interacts very strongly with your catalyst, and that would lead that you are losing the surface that is actually active for your desired reaction. This sometimes happens when you have sulfur impurities. So this is something very relevant when you are looking at petrochemical processes involving gases, also biogas impurities that can have sulfur and other compounds that adsorb specifically on your most active sites for the actually otherwise desired reaction. And to prevent these poisonings, you could, for example, clean your gases to remove these impurities. Or you can also develop tolerant catalysts. Sometimes you can regenerate, like desorb your poisons. However, the nature is often, the disturbing nature in your reaction is that it's a very strong interaction, so it's very difficult to remove them completely. So either cleaning or tolerant materials, catalyst materials, are the solution. Finally, the loss over gas phase is just that the active functional groups potentially are disappearing, where you just, of course, lose activity. And there is here an example for a catalyst for oxidation of hydrocarbon. And what you typically do is you are adding stabilizing promoters that keep your functional groups tighter on the surface and prevent from disappearing. It is very difficult to replenish the surface with these groups because they typically have to be introduced while making the catalyst. To summarize catalysts or heterogeneous catalysts, the majority of industrial processes rely on heterogeneous catalysis, where the characteristics is that the active sites are on the surface. They must be accessible to the reactants. We can tailor the properties by choice of materials and by structuring. To know if we have arrived at the right properties, we need to characterize the catalyst, and there is a huge range of methodology to do so. And that we just have to select for the right method for the right problem. Do we just need to have the surface area? Do we need certain functional groups and so forth? So we have to select the right methodology. Catalysts typically don't last forever, so we need to know what can happen and what degradation or deactivation mechanisms we have, and we have many opportunities to avoid, prevent, or diminish them by choice of system, design of reactor, by choosing operating conditions. And just as a final message, catalysts must not last forever. So we can also cope with different degrees of deactivation over time. It is just need to know what is actually happening in detail so we can tailor the right system and system conditions. With that, I am finished with my catalysts introduction. Thank you for your attention.